How the moon formed. Since the dawn of human civilization, the moon has captivated our imagination. Its silvery glow has guided travelers, inspired poets, and marked the passage of time. Yet, behind its serene and beautiful appearance lies a violent and fascinating history, a story of cosmic collisions, molten rock, and the formation of a celestial companion that would forever change the dynamics of our planet. Understanding how the moon formed is not just a tale of rocks and gravity. It is a window into the very processes that shaped the early solar system. The moon is unique in many ways. Unlike the moons of other planets, it is relatively large compared to the size of its host planet. Its composition, orbital characteristics, and internal structure all point to a tumultuous origin. For decades, scientists debated its formation, proposing various theories, from co-formation alongside Earth to the capture of a wandering celestial body. However, the most widely accepted explanation today is the giant impact hypothesis, a theory that combines destruction with creation on a scale that is difficult to imagine. According to this hypothesis, the moon formed approximately 4.5 billion years ago. In the earliest days of the solar system, Earth itself was still in its infancy, a molten world shaped by countless collisions with other planetesimals. It was during this chaotic time that a Mars-sized body, often referred to as Theia, collided with the proto-Earth. The impact was catastrophic. Enormous amounts of debris were ejected into orbit around Earth. Vaporized rock and molten fragments mingled, and a disk of material began to coalesce. Over millions of years, gravity pulled this material together, forming a spherical body, the moon. Evidence for this dramatic origin is all around us. The isotopic composition of moon rocks, brought back by the Apollo missions, is remarkably similar to Earth's mantle. This suggests that the moon is made largely of material that once belonged to our planet, rather than being a captured object from elsewhere in the solar system. Its relatively small iron core and lower density compared to Earth also align with the idea that it formed from the outer layers of the proto-Earth and Theia, rather than from a fully differentiated planetary body. The giant impact not only created the moon but also had profound consequences for Earth itself. The immense energy released by the collision may have melted large portions of the Earth's surface, influencing the differentiation of the core, mantle, and crust. The newly formed moon exerted gravitational forces on Earth that would eventually stabilize the planet's axial tilt, giving rise to a more stable climate and seasonal cycles. These gravitational interactions continue to this day, as the moon's presence regulates tides and subtly slows Earth's rotation, elongating our days over billions of years. The moon's formation was not an instantaneous event, but a prolonged process. After the initial coalescence, the moon remained partially molten, forming a magma ocean across its surface. This molten layer slowly crystallized over hundreds of millions of years, giving rise to the highlands and the darker basaltic plains we observe today, known as lunar Maria. Each crater and mountain on the moon's surface tells a story of subsequent collisions, volcanic activity, and the relentless bombardment by meteoroids that have shaped its visage over eons. Understanding how the moon formed also provides insight into planetary systems beyond our own. The processes that led to its creation, massive impacts, debris disks, and accretion of material are fundamental mechanisms that likely occur throughout the universe. By studying the moon, we gain a template for understanding satellite formation, the evolution of planetary bodies, and the violent yet creative nature of cosmic evolution. In conclusion, the moon is far more than a glowing orb in our night sky. It is a testament to the violent and dynamic forces that shaped the early Earth and the solar system at large. Its very existence is a reminder that creation often emerges from destruction, that celestial violence can yield stability, and that the seemingly tranquil beauty of the moon masks a history of extraordinary cosmic events. Every phase of the moon, every crater and ridge, carries the echoes of a giant impact that changed the destiny of our planet forever. In contemplating the moon's origin, we are not merely looking at a satellite. We are glimpsing the formative forces of the universe itself. They impact billions of years ago, in the formative years of our solar system, a cataclysmic event unfolded that would forever alter the trajectory of our planet and give rise to a celestial companion that has guided humanity ever since. This event is known as the Theia impact, a monumental collision between the young Earth and a Mars-sized protoplanet named Theia. While today it exists primarily as a scientific hypothesis, the evidence supporting this extraordinary encounter is compelling, revealing a story of cosmic violence, creation, and the delicate balance of forces that shape planetary evolution. They, a massive protoplanet wandering in the early solar system, collided with the proto-Earth approximately 4.5 billion years ago. At that time, the solar system was a chaotic environment filled with countless planetesimals and emerging planetary bodies. The young Earth was still molten in many regions, constantly reshaped by smaller impacts. They, moving along its orbit, struck Earth at an oblique angle, unleashing unimaginable energy in a collision that was both destructive and formative. The force of this impact was so immense that it vaporized parts of the two bodies, sending molten rock, metal, and debris into orbit around the Earth. The aftermath of the Theia impact was dramatic. The material ejected into space formed a circumplanetary disk, composed of fragments from both the proto-Earth and Theia. Over millions of years, this debris gradually coalesced under its own gravity, forming a single spherical body that became the Moon. This scenario explains why the isotopic composition of lunar rocks closely resembles that of Earth's mantle, a key piece of evidence that supports the giant impact hypothesis. The Moon, therefore, is not just a passive observer of Earth's history. It is a product of one of the most extraordinary collisions in our solar system. The energy released by the Theia impact reshaped Earth in profound ways. The molten surface of the planet was redistributed, aiding in the differentiation of the core, mantle, and crust. This violent event may have also contributed to the early atmosphere by releasing volatile compounds, some of which would later play a critical role in the emergence of life. The impact fundamentally influenced Earth's rotational dynamics, setting the planet on a path toward its current day length and stabilizing its axial tilt factors that would prove essential for the development of a stable climate and the eventual flourishing of life. They impact studying the impact also offers a window into the processes that govern planetary formation and satellite creation throughout the universe. Massive collisions were common in the early solar system, shaping planets, moons, and asteroids alike. Yet, few events were as consequential as the encounter between Earth and Theia. By examining the Moon's structure, its orbit, and the chemical similarities with Earth, scientists have reconstructed this ancient event, providing insights not only into our own planet's history, but also into the dynamics of other planetary systems. The impact was not a singular, instantaneous moment, but the beginning of a long evolutionary process. The Moon initially existed as a partially molten body, with its surface covered in a global magma ocean. Over time, as it cooled and solidified, its surface features craters, highlands, and meriae emerged, each bearing witness to subsequent meteoroid impacts and volcanic activity. The enduring scars on the Moon's surface serve as a cosmic record of both the Theia impact and the ongoing bombardment that has shaped the inner solar system. The Theia impact is a testament to the duality of destruction and creation. While the collision was catastrophic, it ultimately resulted in the formation of the Moon, a satellite that plays a crucial role in Earth's environmental stability. Tides, climate regulation, and even the synchronization of day and night cycles are influenced by the Moon's gravitational presence, a direct consequence of that ancient, violent encounter. Without Theia's fateful collision, Earth may have lacked the stabilizing forces necessary to support complex life, and the Moon that has inspired countless cultures, myths, and scientific inquiry might never have existed. In essence, the Theia impact illustrates the incredible forces at play in our universe. It highlights how planetary formation is not a gentle process but a chaotic ballet of collisions, accretion, and gravitational interplay. It underscores the fact that even moments of extreme violence in space can yield outcomes of remarkable beauty and significance. Today, as we gaze at the Moon from Earth, we are witnessing the result of an extraordinary cosmic event, a silent testimony to the power, unpredictability, and creativity of the universe. In conclusion, the Theia impact was more than just a collision. It was a transformative event that shaped the destiny of Earth and its satellite. The Moon's existence, its composition, and its influence on our planet are enduring reminders of the violent yet creative forces that have governed the evolution of the solar system. Each crater, each ridge, each phase of the Moon tells a story that began with a catastrophic impact billions of years ago, a story of destruction, formation, and the emergence of a celestial companion that continues to define life on Earth. Water on Earth, water the essence of life, the silent sculptor of landscapes, and the driving force behind countless biological and geological processes, has not always been a defining feature of our planet. Today, it covers approximately 71% of Earth's surface, existing in oceans, rivers, lakes, ice caps, and the atmosphere. Yet, the story of how water came to Earth is a tale as ancient and complex as the formation of the planet itself, intertwined with cosmic collisions, planetary evolution, and the delicate balance of chemistry and physics that made our world habitable. The origin of water on Earth is a topic that has fascinated scientists for centuries. Unlike other planets in our solar system, Earth possesses abundant liquid water, a fact that is essential for life. Early theories suggested that water was released from Earth's interior through volcanic outgassing, while more recent studies emphasize the importance of extraterrestrial delivery. Meteoroids, comets, and asteroids, carrying ice and hydrated minerals, bombarded the young Earth during its formative years, depositing water that would accumulate over millions of years. This cosmic delivery system illustrates the intimate connection between Earth and the broader solar system, revealing that the origins of life may have been seeded by interplanetary materials. Volcanic activity played a crucial role in shaping Earth's hydrosphere. As molten rock erupted from the interior, it released gases, including water vapor, into the atmosphere. Over time, this water vapor cooled, condensed, and fell as precipitation, gradually filling basins that would become the first oceans. This process, known as outgassing, was instrumental in forming the early atmosphere and initiating the hydrological Sekolah system that would regulate temperature, weather, and climate for billions of years. The interplay between volcanism, atmospheric development, and water accumulation was a delicate balance, with each component influencing the others in profound ways. The delivery of water from space was not uniform but occurred over billions of years through countless impacts. Carbonaceous asteroids, in particular, were rich in hydrated minerals, contributing significant quantities of water to Earth's surface. Comets, composed largely of ice and organic compounds, also played a role, though their contribution is still debated. These extraterrestrial sources, combined with volcanic outgassing, created a dynamic and evolving system, slowly saturating Earth with the water that would sustain life and shape the planet's surface. Once water accumulated, it began to reshape Earth's landscapes. Early oceans absorbed heat, stabilized the climate, and acted as chemical reactors, facilitating reactions that eventually led to the emergence of life. The presence of water allowed minerals to dissolve, erode, and form sedimentary rocks, leaving geological records that provide crucial evidence of Earth's early environment. Tectonic activity, driven by heat from Earth's interior, recycled these rocks, further influencing the distribution and chemical composition of water on the planet. Water on Earth is also intimately linked with the planet's magnetic field and atmospheric protection. The magnetic field shields the atmosphere from solar wind, preventing the loss of volatile compounds, including water vapor, to space. Without this protective shield, Earth might have experienced the fate of Mars, where much of the water was stripped away over time, leaving the planet dry and barren. The presence of a stable magnetic field, combined with water delivery and retention mechanisms, underscores the remarkable convergence of factors that allowed Earth to become a habitable world. The chemical composition of Earth's water provides further insights into its origins. Studies of isotopic ratios, such as deuterium to hydrogen, allow scientists to trace the sources of water. Comparisons with cometary ice and carbonaceous chondrites suggest a combination of terrestrial and extraterrestrial contributions, painting a picture of a planet shaped by both internal and external forces. This blending of sources demonstrates the complexity of planetary evolution, where multiple processes converge to create conditions suitable for life. The existence of water set the stage for one of the most critical events in Earth's history, the emergence of life. Simple molecules dissolved in oceans created primordial soups, reacting under the influence of energy sources such as sunlight, volcanic heat, and electrical discharges. These reactions eventually led to the formation of complex organic molecules, the building blocks of life. Without the presence of abundant, stable water, Earth's biosphere, as we know it, could never have developed. Water is not merely a component of life. It is its medium, its sustainer, and the environment in which evolution has unfolded for billions of years. In conclusion, the story of water on Earth is a saga of cosmic chance, planetary processes, and chemical serendipity. It is a narrative that spans billions of years, beginning with the violent formation of the solar system, the bombardment of asteroids and comets, the release of gases from a molten planet, and the gradual accumulation of oceans that shaped Earth's climate geology, and biology. Every drop of water, every ocean current, and every raindrop carries within it the echoes of the universe's formative events, reminding us that the Earth we inhabit today is the product of intricate and extraordinary processes. Water is not just a resource, it is the legacy of cosmic history, a reminder of Earth's origins, and the foundation of life itself. Cooling of Earth. In the earliest days of our planet, Earth was a world of extreme chaos and fire. Its surface, molten and turbulent, glowed with incandescent heat as collisions from meteoroids, asteroids, and planetary fragments continued to bombard the young planet. This primordial inferno was the crucible in which our planet's crust, atmosphere, and hydrosphere were forged. Yet, over millions of years, the Earth gradually cooled, transitioning from a searing molten sphere to a solid planet capable of supporting the processes that would ultimately lead to life. Understanding this cooling process provides profound insight into Earth's formation, geological evolution, and the delicate balance that allows it to sustain life today. The process of Earth's cooling was influenced by both internal and external factors. Internally, radioactive decay within the planet's core released vast amounts of heat. Elements such as uranium, thorium, and potassium generated energy, keeping the interior molten even as the surface began to solidify. Convection currents within the mantle transferred heat toward the surface, gradually forming a thin, rigid crust over the molten interior. This crust, fragile and constantly reshaped by volcanic activity and tectonic movements, marked the planet's first step toward stability. Over millions of years, the gradual dissipation of heat allowed the surface to cool enough for liquid water to accumulate, setting the stage for oceans and the emergence of life. Externally, the Earth's interactions with space played a critical role in its thermal evolution. The bombardment of meteoroids and asteroids, remnants of the solar system's formation, delivered additional heat with every collision. These impacts melted localized regions of the crust, sometimes even creating transient magma oceans. Yet, paradoxically, they also delivered water, organic molecules, and other materials that would aid in the eventual stabilization of Earth's surface. As the frequency of these impacts decreased over time, the planet was able to retain heat more efficiently, gradually establishing a balance between internal heat production and radiative cooling to space. Volcanism was another key mechanism in Earth's cooling. The eruption of molten rock from deep within the mantle served as a release valve for internal heat. Lava flows and volcanic outgassing contributed to the formation of the atmosphere, releasing water vapor, carbon dioxide, and other gases. These processes not only regulated temperature, but also played a pivotal role in the development of a hydrosphere, as condensed water vapor eventually formed the first bodies of water. Volcanoes, therefore, were both a source of heat and a mechanism for cooling, illustrating the dynamic interplay of forces that shaped early Earth. The cooling of Earth also set in motion the processes of tectonics. As the crust solidified, it began to fracture and move, giving rise to the first continental masses and ocean basins. Plate tectonics facilitated the recycling of rocks, minerals, and volatiles, further influencing the thermal evolution of the planet. Subduction zones allowed molten material to sink back into the mantle, while rising plumes of magma brought heat to the surface. This constant movement of lithospheric plates not only redistributed thermal energy, but also created the diverse geological features that characterize Earth today. A critical milestone in the cooling process was the formation of a stable lithosphere and a temperate surface environment. As Earth's surface temperatures decreased, conditions became favorable for the condensation of water vapor, initiating rainfall and the formation of early oceans. These bodies of water acted as thermal buffers, absorbing solar radiation and distributing heat around the planet. The oceans became key regulators of Earth's climate, stabilizing temperatures and facilitating chemical reactions that would ultimately lead to the development of life. Without this gradual cooling, the planet would have remained inhospitable, a molten wasteland incapable of supporting biological systems. The cooling of Earth also had profound implications for the planet's magnetic field. As the core partially solidified, convective currents within the liquid outer core generated the geodynamo effect, producing a magnetic field that shields the planet from solar and cosmic radiation. This protective barrier ensured that volatiles, including water, remained in the atmosphere and at the surface, preserving the conditions necessary for life to flourish. In this way, thermal evolution, tectonics, and magnetic field generation are intricately linked, demonstrating the interconnectedness of planetary processes. In conclusion, the cooling of Earth was a complex, multi-layered process that transformed a molten, chaotic world into a stable, life-supporting planet. Internal heat from radioactive decay, external bombardments, volcanic activity, tectonic movements, and ocean formation all played critical roles in regulating temperature and shaping the surface environment. This gradual transition allowed Earth to retain water, develop an atmosphere, stabilize its crust, and create conditions conducive to life. The story of Earth's cooling is not merely a tale of heat loss. It is a narrative of transformation, resilience, and the delicate balance of forces that made our planet the cradle of life. Every continent, every ocean, and every geological feature bears the imprint of this ancient cooling process, reminding us of the dynamic forces that continue to shape our world billions of years after its fiery birth. Volcanic era. In the early history of our planet, Earth was not the serene blue and green world we know today. Instead, it was a realm of fire and turbulence, dominated by volcanic activity on an unprecedented scale. This period, often referred to as the Volcanic era, shaped the planet's surface, atmosphere, and oceans, creating conditions that would ultimately allow life to emerge. Understanding the volcanic era is essential to grasp how geological and chemical processes combined to transform Earth from a molten landscape into a habitable world. During this era, which spanned hundreds of millions of years, massive volcanic eruptions reshaped the young Earth. Molten rock, gases, and ash were expelled from the planet's interior, building mountains, forming plateaus, and creating new crust. These eruptions were not isolated events. They occurred globally, affecting the entire planet. Lava flows covered vast expanses, while pyroclastic materials, fragmented rock, ash, and gas were hurled into the atmosphere, influencing climate and atmospheric composition. The intensity and frequency of these eruptions far exceeded what we observe today, reflecting the extreme internal heat and dynamic tectonics of early Earth. Volcanism during this era played a critical role in shaping the atmosphere. Gases released from magma, including water vapor, carbon dioxide, nitrogen, and trace amounts of other compounds, contributed to the formation of a thick, greenhouse-rich atmosphere. water vapor eventually condensed into liquid, filling basins and forming the first oceans, while carbon dioxide helped regulate temperatures, maintaining a balance that allowed liquid water to persist. Volcanic gases also carried minerals and nutrients into the oceans, laying the groundwork for chemical reactions that would eventually give rise to organic compounds and life. The volcanic era was not merely a geological phenomenon. It was a period of planetary evolution. The immense heat from magma chambers and volcanic eruptions drove mantle convection, which in turn fueled plate tectonics. As the lithosphere moved and collided, continents began to form, ocean basins deepened, and the crust became increasingly complex. Volcanoes served as both creators and destroyers, forming land masses, while simultaneously reshaping them with lava flows, eruptions, and pyroclastic events. This relentless cycle of destruction and creation was critical in establishing the geological diversity we observe on Earth today. Volcanism also had profound effects on Earth's hydrosphere. The release of water vapor into the atmosphere contributed to rainfall, which eroded volcanic rocks and carried minerals into developing oceans. These processes enriched early oceans with chemical compounds that facilitated prebiotic reactions, setting the stage for life. Additionally, volcanic islands that emerged from the ocean provided habitats for early microbial life and contributed to the planet's evolving ecosystems. In this way, volcanic activity was intimately linked with the development of Earth's biosphere. Impact events during the volcanic era further intensified geological activity. Meteoroid and asteroid collisions, remnants of the solar system's formation, triggered localized or global volcanic eruptions, amplifying heat flow and crustal melting. These impacts, combined with internal tectonic processes, created a dynamic environment in which the planet's surface was constantly renewed. This era of heightened geological activity ensured that Earth remained chemically active, recycling elements, forming new crust, and maintaining the delicate balance required for long-term habitability. Volcanic activity during this period also influenced Earth's magnetic field. The convection of molten iron within the outer core, coupled with thermal energy from the mantle, generated the geodynamo effect that protects the planet from harmful solar radiation. This magnetic shield was crucial for retaining the atmosphere, preserving water, and enabling the chemical processes necessary for life. Thus, volcanism not only shaped the surface, but also contributed indirectly to planetary protection and environmental stability. In conclusion, the volcanic era was a defining chapter in Earth's history. It transformed a molten, unstable planet into one with oceans, continents, and a dynamic atmosphere. Volcanoes sculpted landscapes, enriched oceans, stabilized climates, and influenced the magnetic field, creating conditions that would eventually allow life to flourish. This period demonstrates the profound interplay between internal heat, tectonics, atmospheric chemistry, and planetary evolution. Every mountain, island, and volcanic plain is a reminder of this fiery epoch, a testament to the power of volcanism and the extraordinary processes that shaped the Earth into the planet we inhabit today. Formation of oceans. The oceans, vast and enigmatic, cover over 70% of Earth's surface. Yet their formation was a complex and prolonged process that spanned millions of years. The story of how Earth's oceans came into being is intertwined with the planet's volcanic activity, atmospheric evolution, and extraterrestrial contributions. Understanding the formation of oceans is crucial not only for comprehending Earth's geological history, but also for appreciating the conditions that made the emergence of life possible. In the earliest stages of Earth's history, the planet's surface was dominated by molten rock, constant bombardment from meteoroids, and intense volcanic eruptions. Water, as we know it, did not exist in stable, liquid form. Instead, it was present in the form of vapor within the atmosphere, or locked within hydrated minerals. Volcanic outgassing released vast quantities of water vapor, carbon dioxide, and other gases into the atmosphere. As the planet gradually cooled, this water vapor condensed, initiating the first rainfalls that would accumulate in low-lying basins, forming nascent oceans. These primitive bodies of water marked the beginning of Earth's hydrosphere, a critical component for life and climate regulation. While volcanic outgassing contributed significantly to the accumulation of water, extraterrestrial sources played a crucial role as well. Comets, composed largely of ice, and carbonaceous asteroids, rich in hydrated minerals, bombarded the young Earth, delivering additional water and organic compounds. These cosmic deliveries, often occurring during periods of heavy bombardment, augmented the Earth's early water inventory and enriched it with chemical precursors essential for prebiotic chemistry. This interplay between terrestrial and extraterrestrial processes highlights the interconnected nature of planetary evolution, where both internal and external forces shaped the oceans. The cooling of Earth's surface was another critical factor in ocean formation. Initially, the planet was so hot that any water present would have existed as vapor over millions of years. As the surface temperature declined, condensation became possible. Rainfall began to accumulate, gradually filling basins and creating continuous bodies of water. These early oceans acted as thermal buffers, absorbing solar radiation, moderating temperatures, and stabilizing the climate. By distributing heat around the planet, the oceans enabled the development of a more hospitable environment for life and facilitated chemical reactions necessary for the synthesis of organic molecules. The chemical composition of early oceans was influenced by the interaction of water with newly formed rocks and minerals. As rainwater eroded volcanic landscapes, it carried dissolved minerals and nutrients into the basins, enriching the oceans with elements such as calcium, magnesium, and potassium. This process, known as chemical weathering, played a critical role in establishing the geochemical cycles that continue to govern Earth's oceans today. The dissolved minerals not only provided essential components for early life, but also contributed to the formation of sedimentary rocks, which preserved records of Earth's evolving environment. Tectonic activity further shaped the oceans by influencing the formation of basins, continental margins, and oceanic ridges. The movement of lithospheric plates created depressions that could hold water, while mid-ocean ridges generated new crust, gradually expanding ocean basins. Volcanic islands emerged, providing additional surfaces for water accumulation and influencing local hydrology. Subduction zones recycled water into the mantle, creating a dynamic system where water continually interacted with the planet's interior. This intricate balance between tectonics, volcanism, and hydrology ensured the long-term stability of Earth's oceans. The formation of oceans also had profound implications for Earth's atmosphere and climate. By absorbing carbon dioxide and other greenhouse gases, oceans helped regulate global temperatures, preventing the planet from overheating or freezing. Ocean currents distributed heat across the globe, influencing climate patterns and fostering the development of diverse habitats. These processes set the stage for the eventual emergence of life, providing stable, nutrient-rich environments in which early microorganisms could thrive. In conclusion, the formation of Earth's oceans was a monumental achievement in planetary evolution. It was the result of a delicate interplay between volcanic outgassing, extraterrestrial water delivery, cooling of the planet, chemical weathering, and tectonic activity. These processes transformed a molten, inhospitable world into one with vast, life-sustaining oceans. Every drop of water, every current, and every oceanic trench carries the story of billions of years of geological and chemical processes. The oceans are not merely bodies of water. They are the living, dynamic record of Earth's history, the cradle of life, and a testament to the extraordinary processes that shaped our planet. Clouds the ethereal, ever-changing formations that float gracefully across Earth's sky are far more than mere visual spectacles. They are vital components of the planet's climate system, acting as regulators of temperature, reservoirs of water, and engines of weather patterns. Understanding clouds, their formation, and their role in Earth's hydrological and climatic systems provides a profound insight into the delicate balance that sustains life on our planet. The formation of clouds begins with water vapor, the invisible gaseous form of water, which rises from oceans, rivers, lakes, and moist soil through the process of evaporation. Solar energy drives this evaporation, causing molecules to escape into the atmosphere. As this warm, moist air ascends, it encounters lower pressure and cooler temperatures, resulting in condensation, the transformation of water vapor into tiny liquid droplets or ice crystals. These microscopic particles cluster together around dust, pollen, or other aerosols, forming clouds. This process, though seemingly simple, is a complex interplay of thermodynamics, atmospheric chemistry, and fluid dynamics, revealing the intricate mechanisms that govern Earth's atmosphere. Clouds exist in a remarkable diversity of forms and altitudes, each with unique characteristics and roles. Cirrus clouds, wispy and high in the stratosphere, are composed primarily of ice crystals and often indicate approaching weather systems. Cumulus clouds, puffy and majestic, dominate the lower atmosphere, shaping the sky with their billowing forms. Stratus clouds form extensive, uniform layers that blanket the horizon, while nimbostratus clouds carry moisture, producing steady rainfall. Altocumulus and altostratus clouds inhabit intermediate layers, adding further complexity to the atmospheric tapestry. Each type of cloud interacts with sunlight, heat, and wind, influencing weather and climate in subtle yet profound ways. Clouds play a critical role in regulating Earth's temperature. By reflecting sunlight, they reduce the amount of solar energy that reaches the surface, preventing overheating. Conversely, clouds trap infrared radiation emitted by the Earth, creating a warming effect during the night. This delicate balance between reflection and insolation stabilizes global temperatures, moderates climate, and ensures that ecosystems remain habitable. Changes in cloud cover or composition can dramatically alter climate patterns, highlighting the importance of understanding their behavior in a changing world. The movement of clouds also drives precipitation, a fundamental component of the hydrological cycle. As clouds form and grow, droplets collide, merge, and increase in size. When they become heavy enough, gravity pulls them toward the Earth, releasing water as rain, snow, sleet, or hail, depending on temperature conditions. This precipitation replenishes rivers, lakes, and aquifers, supporting life across terrestrial and aquatic ecosystems. Clouds are thus the vehicles that transport water from oceans to land, distributing it across the globe in a complex network of cycles that sustain life. Clouds also influence weather patterns on a planetary scale. Their interactions with wind currents, temperature gradients, and pressure systems shape storms, monsoons, hurricanes, and cyclones. High-altitude clouds can signal changes in atmospheric circulation, while dense, low-lying clouds can trigger localized storms. Through these processes, clouds act as both indicators and drivers of climate dynamics, linking localized weather phenomena to broader global systems. They are not passive elements of the sky, but active participants in Earth's environmental equilibrium. Beyond their scientific significance, clouds have profoundly influenced human culture and perception. Throughout history, they have inspired art, literature, and spirituality, symbolizing change, impermanence, and transcendence. Yet their scientific importance surpasses their aesthetic value. Understanding clouds allows meteorologists to forecast weather, climatologists to model climate change, and hydrologists to manage water resources. The study of clouds connects atmospheric science, environmental stewardship, and the survival of ecosystems, illustrating their multifaceted role on Earth. In conclusion, clouds are more than fleeting shapes in the sky. They are dynamic, life-sustaining systems, essential to the planet's balance. From the microscopic formation of droplets to their role in regulating climate, distributing water, and driving weather patterns, clouds are indispensable to life on Earth. Their presence reflects the intricate interplay of water, energy, and atmospheric processes that has evolved over billions of years. Each formation, from a delicate cirrus streak to a storm-laden cumulonimbus, tells a story of the planet's water cycle, climate regulation, and the ongoing processes that sustain life. Clouds are, in essence, the visible breath of our planet, a reminder of Earth's dynamic, interconnected, and ever-changing environment. Rain, the gentle patter on rooftops, the rhythmic cascade in forests, and the life-giving deluge over oceans and plains is one of Earth's most vital natural phenomena. It is the culmination of complex atmospheric processes, a critical component of the hydrological cycle, and a primary factor sustaining life across the globe. Understanding rain involves exploring the intricate interplay between clouds, temperature, pressure, and the dynamics of Earth's climate, revealing the delicate balance that ensures the survival of ecosystems and human societies alike. The journey of rain begins with evaporation, a process driven by the sun's energy. Water from oceans, lakes, rivers, and even soil turns into vapor, rising into the atmosphere. Transpiration from plants further contributes to this atmospheric moisture. As this warm, humid air ascends, it cools and reaches a point where condensation occurs, forming clouds composed of countless tiny water droplets or ice crystals. The process of condensation is influenced by atmospheric conditions, the presence of aerosols, and temperature gradients. These clouds, often suspended high above the Earth, are the precursors to precipitation, containing the potential to release stored water in the form of rain. For rain to occur, These microscopic droplets must grow large enough to overcome air resistance and gravitational forces. Within clouds, droplets collide and merge in a process known as coalescence. In colder clouds, ice crystals form, grow, and eventually melt into raindrops as they descend. The size, intensity, and distribution of rainfall are determined by a multitude of factors, including cloud type, atmospheric stability, wind patterns, and temperature profiles. From gentle drizzles to torrential downpours, the variability of rain reflects the complexity of the Earth's atmospheric systems. Rain is not merely a weather event. It is a vital component of the planet's water cycle. When precipitation falls to the surface, it replenishes rivers, lakes, aquifers, and wetlands, sustaining ecosystems and enabling plant growth. Rainwater percolates through soil, facilitating nutrient transport and maintaining fertile grounds for agriculture. In mountainous regions, rain contributes to the formation of streams and rivers, which eventually feed into larger water bodies, creating a network of freshwater systems essential for both human and ecological survival. The distribution and timing of rain are crucial in determining the productivity of forests, grasslands, and croplands, emphasizing its central role in sustaining life on Earth. Rain also plays a critical role in climate regulation by transferring heat and moisture within the atmosphere. It helps to balance temperatures across regions and influences weather patterns. Rainfall interacts with oceans, influencing currents and atmospheric circulation, while localized. Precipitation events shape microclimates. The interaction between rain, vegetation, and soil further regulates atmospheric humidity, creating feedback mechanisms that maintain ecological stability. In this sense, rain is both a product and a driver of Earth's complex climate system. Throughout history, rain has had profound impacts on human civilization. Societies have relied on predictable rainfall for agriculture, the sustenance of populations, and the management of water resources. Monsoon systems in Asia, seasonal rains in Africa, and temperate precipitation patterns in Europe and the Americas have dictated agricultural cycles and shaped cultural practices. Conversely, the absence of rain, as seen in droughts, can lead to famine, economic hardship, and environmental stress, highlighting the delicate balance between human life and this vital natural phenomenon. Beyond its practical and ecological importance, rain carries symbolic and cultural significance. It has been celebrated in myths, literature, and art, representing fertility, renewal, and purification. Yet, scientifically, rain is a testament to the complex interactions between solar energy, the hydrosphere, and atmospheric dynamics. It is a visible manifestation of the water cycle, demonstrating how Earth's systems operate in harmony to sustain life. In conclusion, rain is far more than falling water. It is a fundamental process that sustains the planet's ecosystems, regulates climate, and supports life. From the microscopic formation of droplets in clouds to the vast networks of rivers and aquifers it nourishes, rain reflects the intricate balance of Earth's hydrological and atmospheric systems. Each drop carries within it a story of evaporation, condensation, and precipitation, a cycle that has persisted for billions of years. Rain is both a symbol and a scientific reality of Earth's vitality, a reminder that the planet's dynamic systems are intricately connected and that life as we know it depends upon the continuous and remarkable movement of water from sky to surface. Analysis and summary of the formation and evolution of Earth and its systems, the story of Earth's formation, evolution, and the development of its life-sustaining systems is nothing short of extraordinary. Spanning billions of years, it encompasses cosmic collisions, internal planetary processes, and the intricate interplay between water, rock, and atmosphere. By examining the 10 key stages and phenomena from meteors and the asteroid belt to rain, we gain a comprehensive understanding of how our planet became the unique world we inhabit today. The journey begins with meteors, tiny yet powerful travelers of the cosmos, whose constant bombardment of the early Earth helped shape the planet's surface and contributed materials essential for chemical evolution. These high-speed collisions, though seemingly chaotic, delivered elements and energy, setting the foundation for the complex planetary environment that would later sustain oceans and life. The asteroid belt, a vast collection of rocky and metallic bodies orbiting the Sun between Mars and Jupiter, serves as both a remnant of the solar system's formation and a source of potential impactors. Its existence demonstrates the delicate balance between gravitational forces and the violent events that sculpted the inner planets. The interactions between Earth and these celestial bodies highlight the profound connection between our planet and the broader cosmos. The formation of the Moon represents another critical chapter in Earth's evolution. According to prevailing theories, a Mars-sized body, Theia, collided with the proto-Earth in a cataclysmic impact. This collision ejected massive amounts of debris into orbit, which eventually coalesced to form the Moon. This event not only created our planet's natural satellite, but also played a pivotal role in stabilizing Earth's axial tilt, influencing tides, and regulating climatic patterns over geological timescales. Theia's impact is a stark reminder of how violent, energetic events in the early solar system directly shaped the conditions that made life possible on Earth. Water, the essence of life, emerged through a combination of extraterrestrial delivery and volcanic outgassing. Comets and water-rich asteroids contributed essential volatiles, while Earth's own interior released water vapor through intense volcanic activity. As the planet cooled, condensation formed the first rainfalls, gradually filling basins and giving rise to oceans. These oceans became the cradle for chemical reactions, prebiotic molecules, and eventually, life itself. Without this delicate balance between cosmic delivery, internal processes, and thermal regulation, the hydrosphere that defines Earth today could never have developed. The cooling of Earth was a process intimately linked with its geological and atmospheric evolution. From a molten, unstable planet, Earth gradually solidified, forming a stable lithosphere, moderating surface temperatures, and allowing liquid water to persist. Volcanism continued to regulate heat, release gases, and facilitate the formation of early continents and ocean basins. This cooling process was critical not only for surface stabilization, but also for enabling tectonic activity, which in turn influenced climate, nutrient cycles, and the development of ecosystems. The volcanic era exemplifies the dynamic nature of early Earth. Continuous eruptions reshaped the surface, released gases into the atmosphere, and contributed essential minerals to nascent oceans. Volcanism acted as both a creator and a regulator, building land masses, while releasing water vapor and greenhouse gases that moderated the climate. These processes laid the groundwork for stable oceans, an evolving atmosphere, and the eventual emergence of life. The interconnectedness of volcanism, tectonics, and atmospheric evolution illustrates the complexity of Earth's formative mechanisms. The formation of oceans represents one of the most profound milestones in planetary history. Water accumulated through rainfall, outgassing, and extraterrestrial delivery, filling basins and creating vast, stable bodies of liquid that moderated temperature, regulated climate, and facilitated chemical evolution. Ocean chemistry, enriched by minerals from eroded rocks, provided essential elements for early life. The interaction between oceans, tectonic activity, and atmospheric processes created a dynamic yet balanced system capable of sustaining ecosystems for billions of years. Clouds, ethereal and ever-changing, reflect the continued evolution of Earth's hydrological and climatic systems. Formed by the condensation of water vapor around microscopic particles, clouds regulate temperatures, redistribute heat, and drive precipitation. Different cloud types, cirrus, cumulus, stratus, and their variants perform diverse roles in the atmosphere. From signaling approaching weather systems to influencing planetary energy balance, clouds represent the visible link between Earth's oceans, atmosphere, and climate, demonstrating how the hydrological cycle operates as a coherent, life-supporting system. Finally, rain is the tangible expression of the water cycle in action. Precipitation transports water from the atmosphere back to the surface, replenishing rivers, lakes, and aquifers. It sustains terrestrial and aquatic ecosystems, facilitates nutrient cycles, and regulates temperature and climate. Rain is not merely a weather event. It is a manifestation of the complex interactions between evaporation, condensation, atmospheric dynamics, and planetary systems that have evolved over billions of years. It ensures that life thrives and ecosystems remain resilient in a constantly changing environment. In conclusion, the combined study of meteors, the asteroid belt, the Moon's formation, the Theia impact, water delivery, Earth's cooling, volcanic activity, ocean formation, clouds, and rain paints a holistic picture of our planet's evolution. Each process is interconnected, highlighting the delicate balance of forces that allowed Earth to become a habitable world. The story of these phenomena is not merely historical. It provides critical insight into planetary science, climate dynamics, and the conditions necessary for life. Understanding this interconnected narrative allows humanity to appreciate the fragility and resilience of Earth, reminding us of the importance of stewardship and scientific exploration. Disclaimer: the information presented in this documentary-style analysis is based on current scientific understanding and research. While efforts have been made to ensure accuracy, scientific knowledge is continually evolving. This content is intended for educational and informational purposes only. If you found this documentary enlightening, don't forget to like, subscribe, and share with your friends and family. Stay connected to explore more fascinating stories about Earth, space, and the incredible processes that shape our universe. Your support helps us continue bringing high-quality, educational content to curious minds everywhere.